Welcome, mathematicians. Today we're going to be starting out by looking at volume, by continuing our geometry unit, looking at our three-dimensional shapes that involve circles. So, as you can see by the learning objective, today we are learning to find the volume of cylinders. Two big keywords in there. Number one is, of course, you might recognize we've been talking about cylinders for a while. That shape that has two circular bases connected. Ooh, they're supposed to be two congruent circular bases. Ooh. One more try. Close enough! Good enough! And yeah, use your imagination. And they're connected, so they kind of forms a nice little tube in there. The other big word that I really want us to focus on today is volume. Volume being the capacity of a three-dimensional space. How much stuff you can fit inside any sort of three-dimensional object. For example, I have here a cylinder, right? It has a concentric circles or congruent circles on the bottom and the top, connected by a nice tube. Avoid the dimples. We will ignore those right now. But the volume of this would be how much water you could fill up in here, how much water it can hold. So that's what we mean with volume. And volume is measured very specifically. It is measured by saying how many little cubes we can fit inside of that object. So we measured in terms of cubes, even though it might not be cubes that fit in that, right? This is trying to fit a square peg into a round hole. Is that the saying? I hope so. But we always consider this is the amount of volume that is defined. Like it could be, it's always 1 by 1 by 1. It could be 1 centimeter by 1 centimeter by 1 centimeter, 1 centimeter cubed, or also 1 millimeter, or milliliter is the same amount. It could be 1 mile by 1 mile by 1 mile. That would be 1 mile cubed. It's a large amount of space that we'd be talking about. But we're really looking at how many of these will fit inside our object. How many could we cram in there, even if that means that we need to cut that piece, this little cube apart. If we can use all parts of it, that still makes it works. So let's start by looking at a cylinder. Let's investigate a cylinder. So I've drawn here a nice kind of flattened cylinder for us. It almost looks like a disc. Notice that I've given us a height of 1 unit. It's only 1 unit high. I don't care what that unit is. It could be miles, it could be millimeters, but it is 1 high. And I've given us, I'll circle in orange real quick, I've given us this little thing, which we're going to kind of imagine is that 1 cube that fits in there. So I'm showing us that one of those definitely fits. The question is, how many more can we put in? So in order to investigate that, I want to say, well, what amount of space is that taking up on the bottom? Certainly it's going to fill up all the way from the top to the bottom of the cube, 1 unit high. That makes sense. But the real question is, how many more of these could I fit in next to it until all of this base is full? Well, because this is a 1 by 1 by 1 unit, right? This is 1 across of a length and 1 deep, I would say, for my depth. So that's covering an area of 1, right? It's just a little square base down here. So I need to cover up the entire base of my lovely cylinder, my little disc. So how big is the base of my disc? We know how to do that. This disc only has a base of a circle. We know that because it's the definition of our cylinder. So let's go ahead and define, it must have some sort of radius, which we'll call r. So I'm just going to leave it as generic as r, which means the area of this entire base in here is going to be pi r squared, the area of the circle. So I need to cover up this amount of base. That's how many cubes then fits in there. I can fit pi r cubed in there. Each one of those little cubes takes up 1 until I fill up pi r squared. If my radius was 1, then I would need pi of those cubes to fill it up. And because they're 1 unit, we're just counting the cubes. We don't have to worry about stacking them on top of each other at all. Not an issue, right? We don't need that at all. So we're just counting up this single layer. Okay, so that means the volume of this, how many cubes can fit into this disk, is simply going to be pi r squared. Just the area of that base. Let's go ahead and see if we can generalize this a little bit more, because there is this constraint here, and not everything's going to be 1 unit. So let's look at another cylinder real quick. Whoop. Here we go. Here's a nice new cylinder to take a peek at. So notice this cylinder, instead of being 1 unit high, it's now 4 units high. Still looks pretty similar otherwise. We have that radius of r. The only thing that's changed is really the height. So here's what I did. I decided, okay, if that's 4 units high, that's really just stacking the disk that we had before with 1 unit on top of itself 4 times. So here you can see, like this guy on the bottom, that's like one of the disks from above. And now all I've done is I've just stacked it. So I have 1, 2, 3, 4 of those disks. 1 unit, this would be 2 units, 3 units, and now 4 units high. So that should be the same thing. All I did is I sliced it into pieces. But I know the volume of each of those little disks with a height of 1. Each of these has a volume of pi r squared. So let's go ahead and put that down. These are my volumes for each of those 4 disks. So now the question is, what is the volume of the total? I just need to sum these pieces together, right? They're additive. I've literally just stacked them on top of each other. If there's pi r squared cubes that fit in the lower disk, and there are pi r squared cubes that fit in the upper disk, and pi r squared cubes that fit in the third and in the second disk, I'm just going to add all of those for a total number of cubes that I would have to use. That's 1, 2, 3, 4 pi r squared. So now the question is, where did that 4 come from again? Where is this 4? Where would we find that in the original picture? Oh, there's a 4. So notice that I just split my height into stacks. And notice that then I just had to add these same numbers together. When we have repeated addition, we call that multiplication. So what I'm really just doing is multiplying by the height. So now we can actually not just say that the volume of this specific cylinder is pi r squared times 4, because I had 4 stacks that I had to make out of it. I repeatedly added together pi r squared 4 times. I can also say in general, so we're going to call this generalized, the volume of a cylinder is going to be that same thing, that pi r squared. But now you can imagine if I had more stacks, if I had 6 stacks, I would have to multiply this by 6, because I would have 6 disks stacked on top of each other. If I only had 2 stacks, I would just multiply it by 2. I would just double that amount. So whatever the height is, I'm just going to multiply by that. So this would be my generic and powerful formula for the volume of a cylinder. Let's put it to the test. So let's grab this guy so I can refer to it down below in our example. Oh, okay, sure. You can put it back up there. Ah! Okay, well, I lost a y, but other than that, we seem to be okay. Shala. Oops, that's the wrong color. And there we go. So we're going to be using this formula. But now we're going to be using it on this sort of a cylinder, which you can see looks a little bit different. All I did is I took our cylinder that normally sits like this on top of its 2 circular bases, and I tipped it over. Otherwise it looks like the same shape. The orientation doesn't really matter. However, we will have to be careful about what we define to be our radius and our height. So notice that the base is still going to be the 2 circles. That's defined to be our basis. It's not like this little tiny edge that's down here. Even though that's kind of what you would imagine would be resting on, we're going to talk about the base as one of the circles. So our radius, again, is from the middle of that circle, let's grab black, to the outer edge. I've given us 3 inches as all the way across. That's the diameter. So in order to talk about the radius, I need to split that diameter in half. So the diameter in half, that would be 3 divided by 2 is 1.5, or you can leave it as 3 halves. That's totally fine. But 1.5 inches is our radius. Oops. Radius. There we go. I'm going to bubble this because I know I'm going to need that. I need 2 things to determine the volume, a radius and a height. Radius is one of them. Now let's talk about the height. The height, you might be tempted to say, is 3 inches. I know, I would be tempted to say that this is 3 inches high as well. However, remember that the orientation of this is a little off. So looking back at what our typical cylinder looks like. The height is the distance between our two circular bases. The distance between our two circular bases here is that 4.5 inches. So that's actually going to be our height in this case. Height is 4.5 inches. Okay, well with that, I am ready to plug in. Let's do it. So, volume of my cylinder, I'm just going to use V for now, is going to be pi. Instead of R, I'm going to write in what I know R is, 1.5 inches squared, times, instead of just H, this specific height is going to be 4.5. I happen to know that 15 times 15 is 225, which means this is tenths times tenths is hundredths, so this would be 2.25 instead of 225 times 4.5. Ooh, let's do side math for this guy because he looks like a fun one to do side math on. I'm going to try to multiply 2 and 25 hundredths by 4.5. And I'm going to do this in a kind of distributive way. So I'm multiplying these guys together. So first thing, I'm just going to multiply that 2.25 times 4. So 4 times 2 is just 8. And then 4 times 25 hundredths. There's 4 quarters and $1, so that's 4 times 25 cents makes 1 whole. And now I'm going to deal with this 1/2 over here. Let's use our rainbow. Now I need 1/2 of this whole number. So 1/2 of 2 makes 1, and 1/2 of 25 is 12.5. Now let's put everything together. 8 plus 1 is 9, plus another 1 is 10, and 125 thousandths. Cool. Nice little side math over there. It was a fun one. 10 and 125 times pi. Cool. So with that, all I need to do is double check what are my units in this guy. Notice I have inches and inches. That means I'm talking about inches cubed. Remember, we're talking about how many cubes we can fit inside some sort of capacity. You can also, so you can leave it like this in terms of pi. That's our exact answer. You can't get more exact like that. That is as accurate as possible. But if you wanted to estimate, if you wanted to do like a little reality check and be like, well, I don't know, how many ice cubes do I need? You probably wouldn't say I need 10 pi ice cubes. You'd probably grab a calculator and put in 10.125 or 10 and 125 thousandths times 3.14 or 3 and 14 hundredths. You can go more exact if you want to, but that gives us 31 and then 793. I'm going to the nearest thousandth, so 739 still inches cubed. Notice that I switched from an exact answer with that equals, I know it's really, really true, to a hand wavy, maybe around 32-ish inches cubed. So there we go. That is how we, I want to use rainbow. But that is how we can apply our volume equation for cylinders. Next up, we're going to be expanding this to look at cones. Happy exploring!